Hi, I'm Lucas.
And we're doing Lab 9, application of the Michelson interferometer.
So in the beginning of the lab, we used the Michelson interferometer and we calibrated it by counting the fringes to figure out what amount the fringes actually moved, how many nanometers the fringes actually moved for each division of the micron by counting 100 fringes and 50 fringes and then seeing how much we moved the micron. And we found out that it was around 400,000 nanometers per division micron.
So for part 2, we were trying to find the wavelength of the green light source, and we do this by looking at fringes through the eyepiece and rotating the micrometer. And this was very difficult because we had aligned the fringes through to count it off the edge of the protractor.
So in part 2 of the lab, we were solving for the wavelength of the green light. And we used this equation. Everything was known except for the wavelength. And then we found a value of 561.8 nanometers, and the actual was 546.1 nanometers.
For the sodium light source, we measured the wavelength similar to how we have been doing this so before. We got the two images aligned using the tip tilt mount and then adjusted the micrometer. For this one, we adjusted the micrometer 0.072 millimeters, which gave us a wavelength of 595 nanometers, which is pretty close to the anticipated value of 589 nanometers.
To measure the refractive index of error, we took we measured various changes in pressure for changes in the fringes as we saw them walk across here. We took those numbers, plugged them into this equation right here. We plug them into this equation to obtain a graph, which is right here. We took the slope of this graph, multiplied it by the by the change in atmospheric pressure in Tucson versus at standard temperature and pressure. Then we added this number to the refractive index of error, STP, and from there we obtained the refractive index of error in Tucson.